You know what I mean. I've been calling it 3.6 and 3.7 for the last 4 years. It's going to be hard to switch. So reflections, there are two types. Type number 1, negative f of x is a vertical reflection. The second type of reflection is less common. Matter of fact, I don't even know if our book goes into it much. This one, it will quite a bit, a vertical reflection. What does it mean, vertical reflection? What's the vertical direction? Over the x-axis. You'll see a lot of this. The other one is still important to know about, but I just don't think you'll see a lot of it. F of negative x. Because this is inside the function, what direction does that affect? Horizontal. So this is a horizontal reflection. Okay. So just a real quick example. What are we on? Example 28 or something? 6. So given f of x equals the square root of x, whose graph, by the way, well, you should know what the graph looks like. I'm not going to graph it for you. What does the square root of x graph look like? Often they ask. Where does it start? Where does it begin? 0, 0. Then we have 1, 1. Then we have 4, 2. There's a couple points. There we go. That's what you're trying to describe with that fancy hand wave, right? This is what the graph looks like. So I want you to graph part A. I want you to graph. Let's do it on the same graph. Graph f of x equals negative square root of x. Because the negative is outside the function is the square root here, so the negative is outside of it. What kind of transformation is that? Or reflection is it? Vertical. So what's the change going to be? Instead of going up and to the right, it goes. This right here is the graph y equals negative square root of x. When we look at both of these together, now doesn't it look like a sideways parabola? All right, last one, then we'll move on to the last part of the lesson. Part B, if I asked you to graph f of x equals square root of negative x. Now you could probably guess what's going to happen to the graph, but I want to talk about this. Because don't we always say, or math teachers, don't we always say you can't square root negative numbers? Don't we say that? True, they're going to be non-real, but when we graph things, we have to use real numbers because we have this real number line here for x. So how's it going to be possible that we graph square root of... We flip it over the y-axis because now we're using negative x values. But what's the opposite of negative x values?
Positive.
Positive. That's why this works. If we have a negative x inside of a square root, that means we have to use negative x values because what's the opposite of a negative? A positive. That's why it works to flip this around the y-axis, so the graph is going to come off in this direction. We can use negative values of x now because we're using the opposite of x. So this graph is y equals square root of negative x. Something to think about here real quick. You don't need to draw this because I don't want you to take the time to do it. If you were to look at this graph, what function would you say it came from? This one right here, just pretend that goes to the origin. It was supposed to go through the origin. What's the equation for this? Y equals x squared. If I ask you to graph this now on the same graph, y equals the opposite of x squared, just based on what we just talked about, if the negative is inside the function, what kind of a reflection is that? Horizontal. But if you took that parabola and reflected it horizontally, what are you going to end up with? Same thing. Why is that? Well, what is the opposite of x squared? It's just x squared, so you end up what you start with. So sometimes the horizontal reflection doesn't affect the graph at all because the graph is already symmetric to the y-axis itself. Okay? Anyway, let's move on. We got to do this next topic rather quickly. The last objective, if you remember, or if you wrote it down, was even or odd functions. Even or odd functions. Okay. Let's talk about even first. A function is even if its graph is symmetric to the y-axis. There's also another criteria. Given some function f of x, okay, if f of negative x is equal to the exact function that you start with. What that means is if I give you a function and I ask you to replace all the x's with negative x's, then all that does is result in the same function that you started with. That results in an even function. For example, show that f of x equals 2x to the fourth minus x squared is even. We need to show that it's an even function. Well, the first thing I had you write down is we can tell if it's even if its graph is symmetric to the y-axis, but we don't know what that graph looks like, nor do we even know how to graph that type of function yet. Okay, so we can't check the graph. If we had a graphing calculator, maybe we could type it in and look at the graph on your calculator. We don't have that. So we can't use this criteria. We don't know the symmetry of the graph. We have to use this algebraic property. Okay? Bless you. So we know that f of x, we have to use this algebraic reasoning here. F of x equals 2x to the fourth minus x squared. What's f of negative x equal to? If I took all the x's of the original function and replaced them with negative x's, it's going to look like this. 2 times negative x to the fourth power minus negative x squared. You follow me so far? But what is negative x to the fourth power? Well, we don't know what x is. But negative x to the fourth power is just negative x times negative x times negative x. But 4 negatives multiplied together make it a positive. What about the opposite of x squared? What happens there? So what we end up with is 2x to the fourth minus x squared. How does that compare to the function we started with? It's exactly the same thing. So I'm going to write equals f of x. So look where we've come. We started with f of negative x right here. But what do we end up with? What is f of negative x equal to? Wasn't it equal to the original function? What does that prove? It proves that this is an even function. And if we were to graph this, because it is an even function, what would the graph look like? Symmetric to the y-axis. Okay? Think back to the quiz we just took. You remember that W-shaped graph? Was that symmetric to the y-axis? Was it the same on both sides of the y-axis? So what was that function? Even. That was an even function. Okay? Those are all even functions. Odd. A function is odd if its graph is symmetric to, now you have to be careful, most students have a tendency to say, well, if that one's symmetric to the y-axis, that's got to be symmetric to the x-axis. Were you thinking that? Be honest. It's okay if you were thinking that. But you have to understand why that's wrong. I want you all to in your mind imagine a graph that's the same on the top and the bottom half of the x-axis. Is that a problem? It's not a function. These are supposed to be functions. And if you have a graph that's symmetric to the x-axis, it's not a function. It wouldn't pass a vertical line test. So it can't be symmetric to the x-axis. It's symmetric to the origin. Okay? This is a little bit harder to tell sometimes. It's easy to spot a graph that's symmetric to the y-axis. Sometimes not as easy to tell if it's symmetric to the origin. Here's a graph that is odd. Here's what it means to be symmetric to the origin. You guys pay close attention. This point right here is the point 2, 8. What's the exact opposite of this point? -2, -8. Well, there's a point on the graph that matches that. This point right here is -2, -8. Every point has a point that's the exact opposite across from the origin. What's the location of this point here? 1, 1. What's the exact opposite of this point? And it's right here. We have -1, -1. That's what it means to be symmetric to the origin. Okay? Does that make sense? You choose any point and say, okay, what's the exact opposite of that point? If I change the sign of the x and y values, then that's where the other points have to be. So that's what it means to be symmetric to the origin. Algebraically, though, here's what happens. Given f of x, f of negative x, it starts the same way. You still have to evaluate the function at negative x. F of negative x this time, however, is not going to result in the exact same function you start with. It's going to result in the exact opposite of the function you started with. F of negative x equals the opposite of f of x. Here's what that may look like. Go ahead. No, that's a good question. I hope it wouldn't. So example 8. Let's have f of x equal to 3x to the third plus x. 3x to the third plus x. And I want you to show this is an odd function. We don't know what the graph looks like, so we can't use the fact that this may be symmetric to the origin. We have to use this algebraic property. So what we need to first evaluate is f of negative x. This becomes 3 times negative x to the third power plus negative x. Now, what is the opposite of x to the third power? It's negative x cubed, right? The opposite of x multiplied 3 times is negative x times negative x times negative. So what I'm asking, does this minus sign disappear or does it stay? It stays. So that first term becomes negative 3x cubed. What about this minus sign? Does it disappear or stay? It also stays. So what we end up with is negative 3x to the third minus x. Is that the exact same thing that we started with? But how do we necessarily show that it's the exact opposite? Pay attention to what I'm about to do, because I'd like you to show it this way as well. What if I factored out a negative sign from that entire expression? Then what would be left over if I factored out a negative sign from each thing? 3x to the third plus x. But what is this now inside the parenthesis? Isn't that the original function? So what we end up with here is negative f of x. So just to recap, we showed this algebraic property. Yes, we started with f of negative x, but what did we end up with? Negative f of x. We ended up with the opposite of the original function. Okay? We started with f of negative x. We ended up with negative f of x. That's the algebraic properties of an odd function. Okay, that finishes 3.5.